Welcome everyone to this webinar that's presented jointly between Pittsburgh Supercomputing Center and D.E. Shaw Research. So we're very fortunate today to have our colleagues from D.E. Shaw Research here with us to present. I'm going to hand it off to Ken McKenzie, who will give the first part of this webinar, and then he'll hand it off to his colleague Avi once he's done. So I'm just, before I hand it off, I'll just say, if you have questions as things are being presented here, just please put your questions in the Zoom chat and we'll be monitoring the chat. And if we can't answer your question directly in the chat, then we'll get the attention of the presenter and ask that question. All right, any questions before we get started? All right, then I'm going to stop my sharing and turn it over to Ken.
Uh-oh. Did that work?
Yes.
Yes.
Excellent. I'm Ken McKenzie with D. Shaw Research. We're going to have lots of time for questions at the end of this talk as well. So you have lots of time to think of questions. I'm here with Avi, Robinson, Mosher, and Parker to talk about, this is really a two-piece talk. One first is just talking about the capabilities of the Anton 3 and sort of how fast it is for planning purposes. And then there's a second part of the talk about enhanced sampling features. There's a small subset of enhanced sampling features that we run on this machine. These are special purpose machines. They're unusual. They're all designed from scratch. They all are completely different. This is the third generation one, but they're all blue on the outside with the same pattern, because the hardest thing about a machine is like deciding what skins it should use. So we decided that once and reused it 3 times, which is kind of hysterical because they're completely different inside. So the timeline of the Anton machines, as I say, this is the third one. We've been building these for 20 years now. I guess that makes me old. So there are 3 generations of machines. If you know anything about building chips, this is a really slow schedule. It's like 5 to 7 years between each chip, and they're kind of completely from scratch design. So we take what we learned from the previous generation and build a whole new machine. They're not really related. It's just come from scratch every time. So the pictures here are of the family size machine in one of our data centers with 512 nodes. That's as big as they get in the front and the back, because the cables in the back are just as cool as the nodes in the front, and a single node board. So what I'm going to tell you about in my half of the talk anyway is a little bit about the architecture, mainly emphasizing that this is a special purpose machine. It's not any kind of general purpose machine. And how fast it is for planning purposes. So here's the architecture of this machine, sort of in one slide from the outside in. So it's a parallel machine with a lot of nodes. Every node is basically one chip, and it's already specialized to the problem. The machine is laid out in 3 dimensions. It's the network is a torus. It's got end-around connections, which exactly matches the periodic boundary conditions that you use to simulate biological systems. And so you take the atoms in your system and you divide them up in the obvious way onto the 3 dimensions of these nodes for simulation purposes. Then if you go inside one of these nodes, each node is a chip. The chip itself is has a large number of processing cores on it. The yellow cores are where most of the processing is done, and the red ones on the edges are for communication. And then it has the wires in the 6 principal directions of the torus. And then the chips are basically wired to each other gluelessly. So there's almost nothing in here but chips and wires, plus power supplies and whatever to keep it fed. So if I dig in one layer, I should say, there's still a lot of parallelism here. There's a lot of processors on this chip. It's 12 columns, 12 rows high and up to 24 columns wide. And actually for reliability purposes, if one processor fails, we can just like turn off that column. So the actual number of working columns on a chip varies from 22 to 24 in practice. We dig into one of these tiles, the tile has in it a slice of the processing. So, and there's two halves to this mirrored, as is pretty conventional in chip design. You want to define it, design as few pieces as possible, and then just replicate them. So the PPIM, the particle-particle interaction module, is doing the near neighbor interactions of van der Waals and electrostatics, which is 90% of the computation in molecular dynamics. And it's a bunch of hardware pipelines with tables. So it's slightly programmable via the tables, but mostly wired to a fixed function. And then the other part of these tiles is the geometry core, which is basically just a processor core, and a piece of the SRAM, a piece of the memory for this, where your atoms and bonds and things get scored. There's also a bond calculator, which is another piece of hardware pipeline, and the bond work is sufficiently small that there's one bond calculator per 2 GCs. It gets shared. So the thing to take away from this is there's a lot of parallelism. So you count up all these cores, there's 2 per thing here. There's that makes about 500 per chip times 64. So there's about 30,000, 32,000 processors per system. I should say PSC has a 4x4x4 torus, 64 nodes. So there's a lot of parallelism, and it's extremely special purpose. Like a lot of the work is being done in special purpose hardware pipelines. This doesn't look like anything, any kind of computer that you've used before. So this is worth a slide just to hammer home the specialized hardware aspects of this. So this is from scratch for molecular dynamics, hardware pipelines, embedded processors, integrated networks. It's not a GPU, it's not an FPGA, that network is not InfiniBand, it's all custom. There's no operating system, there's no virtual memory, there's no floating point. There's barely even any memory, actually. If you count up the SRAM is 128 kilobytes per GC. It adds up to about 4 gigabytes for the entire machine. So it's no bigger than the problem that it needs to run, which is how you make a really fast computer. Basically, you throw away all the memory and replace it with processors. The way you use this in practice is it's like a big coprocessor. So you load your chemical system in there. It runs for a couple hours, gives you trajectories, and then it unloads and gives somebody else a chance. It's like old-fashioned batch processing. And the flip side of specialized hardware is you might ask, why isn't it not all hardware? You know, we did some of this is hardware pipelines. Why not do all of it? Well, first of all, you want to hedge against algorithmic uncertainty, which is to say bugs. And yeah, there are bugs that have to be worked around, some of them kind of entertaining. The other thing is like a processor is a pretty good abstraction around an ALU in memory. So for instance, an FFT is a bunch of butterflies and a bunch of data motion, and having a processor synchronize that doesn't really cost anything. There's also lots of housekeeping tasks, like keeping you lay out atoms on nodes initially, but atoms move around as the simulation runs, and some program has to move the atoms to where they're supposed to be in the simulation. And that's a fair amount of general purpose processing tasks. So yeah, embedded processors are a useful organizational principle. So that's all I want to say about the architecture. There are papers in supercomputing if you want to know more. For performance, this is our favorite way to describe the performance, showing the microseconds per day of simulation speed versus the number of atoms on a log-log plot. So I've just plotted here the six benchmarks that are in the table in the RFP. And so this is really not providing you any more information that is in the RFP, except it's a plot. And plots are way more fun because we can, decorate them different ways. But this is a good planning plot. So if you have a 1,000,000 atom system, like STMV here, it's going to run at about 40 microseconds per day. Or at least that's how it ran when we, in our published benchmark. These public benchmarks are slightly optimistic because they're all running with NVT. Anyway, we'll have some of the decorations get at exactly that. So let me decorate these 6 data points with some more information. So the first thing I want to emphasize is efficiency. If this machine were perfectly efficient, the line would be like at a 45-degree angle. So as you added more atoms, you would get the same amount of like performance per atom. But it's actually not. There's a little bend. There's a little bend to it. Pretty much any parallel machine looks like this. So there's a real sweet spot for this machine where it gets the most efficient performance. It's between about 500,000 and 6 million atoms. The RFP offers you a wider range because Phil twisted our arm into doing that. But the to really use this machine in its best possible mode, you want like 1 million atoms. So that it slows down towards the to the lower end, as does any parallel machine, because it's getting harder and harder to squeeze parallel work out of it. So I mentioned there's like 30,000 processors here. When you only have 100K atoms, that's like 3 atoms per processor. So we're down to like 1 watt per processor. It's kind of amazing we get any speed up at all with that. And at the other extreme, it's starting to run out of memory. So we're having to double pump some of the data structures in the PPM. And in particular, for planning purposes, as you get towards the extremes here, you really start to run out of memory. Like you can run this much, but you can't add extra features. You can't turn on a complicated enhanced sampling scheme and expect to get the full number of atoms. But that really doesn't matter until about 6 million atoms. So there's one decoration. The next decoration is I could show you the Anton 2 performance to see how much better it is than Anton 2, which is getting older and older since there aren't any Anton 2s anymore. But the quick answer about this is it's about 10x faster or about 10x bigger, depending on how you want to use it. So for the same size system, at least if you put the lines in the place where I drew them, you get about 10x the performance for your 300,000 atom system, or you could run a 3 million atom system at the same performance. It's actually a little better than that, but when you could use a 10x line, you always use a 10x line. It just sounds better. The other thing I could do is I can plot to decorate these lines is I can plot what actually happened when we run systems on here. So this is like the rubber actually meeting the road. So in addition to the RFP lines from the Anton 3 RFP and the old Anton 2 thing, I can plot what performance extracted from the database of systems that actually ran both at DesRes, the little circles, and PSC, little thing, the little diamonds. Which gives you a sense of it gives you a sense that there's a certain amount of variance. So the RFP numbers are not perfect. They tend to vary based on how much work you're doing. Some of them are actually really, really bad. I actually looked at these. So these are ones where the trajectory interval is set so small. It's like producing frames every 2 picoseconds when we usually produce frames at a rate of hundreds of picoseconds. So there's definitely ways to ruin your performance. But also there's just kind of a variance. And when I gave this talk last year, I promised that I would, with some trepidation, I would put up PSC numbers when I have them. And I do have PSC numbers from the last 6 months, and they're not terrible. It definitely makes the RFP numbers kind of look like an upper bound, even more than it did on Anton 2. And in our defense, in Anton 2, this was like the RFP from 2016, and then the software got better over time. So some of these actual data points are better than the RFP. That's not happening in Anton 3, but maybe it's because the software is new. If you were an optimist, you would say that the software will get better over time. Phil will tell you that I'm not an optimist. In particular, I'm really embarrassed by these lines here. I think this is one job that's getting slower as it runs. Definitely got to find that and fix that. Anyway, that's about as much as I'm going to tell you about. Oh, I have one more slide of performance, which is I can make the performance universe slide. I can take the same kind of microseconds per day versus atoms per node and put every machine in the world on there, most of which are ours. So there's the 64 node Anton 3. There's also Anton 3 machines that we have internally, like the 512 node one, is yet faster and bigger. But also the rest of the world, which falls into two classes, basically. There's single GPUs or small numbers of GPUs connected with NVLink that follow this curve here, basically. I mean, this isn't the newest one. This is H100, so this is a couple of years old, but it doesn't get much better, much faster. So there's the single GPU line, which is sort of the speed of, it's limited by the rate you can run with one GPU. And then there's supercomputers, which are in fact also GPUs, but tied together. And they really kind of suck, like, because the networks are so slow that you really can't gang together a bunch of GPUs yet. They haven't solved the network thing the way we have. So this is the other reason why Anton running a million atom system on an Anton 3 is a particular joy, because this is a cool 100x faster right in here. And this is a sweet spot compared to the rest of the world that doesn't seem to be going away. Like, the supercomputers are not getting faster, they're actually getting slower. The GPUs are getting faster, but very slowly. And that is it for my part of the talk. You ready, Avi?
I sure am.
Let me stop sharing.
All right. Thank you, Ken, for the handoff there. So Ken has been talking about, I think, primarily the, how awesome Anton is if you were running conventional MD, and how much it can get you in terms of time scales and size scales of your system. Sometimes that's not enough for particular problems you're interested in. Sometimes things are just, really stable in a pose that you isn't the only one you want to explore, and you want to say, for instance, maybe there's two different poses and you want to find out like the relative partitioning between them. And even with the really long time scales we can get to, that's not sufficient to get good statistics on those. So we have a bunch of enhanced sampling approaches that you can use, and I'm going to talk about a few of them here. Pretty much all of the enhanced sampling approaches at DE Shaw Research are based on top of something called time-square sampling, which is a method for doing enhanced sampling that's conceptually related to simulated tempering, which is where you have a bunch of different Hamiltonians that you're having a single simulation trajectory jump back and forth between in a principled way. Simulated tempering, as it is usually done, requires knowing the free energies or having an estimate of the free energies for each of those Hamiltonians, like knowing what the free energy is for your different temperatures or something along those lines. However, time-square sampling is an adaptive algorithm that estimates the free energies at the same time that it's doing its simulated tempering, so you don't need to do that for it. It's an approach that was developed at Desres primarily by Christy Prodescu. It's published. The link in the title in the bottom left here is the paper title. And on the bottom right, we actually have the code for the algorithm released with a little bit of a tutorial if anyone wants to have a look at it. It's a general approach that can be applied to many things. But so for simulated tempering, temperature tempering in particular, imagine you've got this energy landscape here with represented by the black line at a sort of lowish temperature, and your simulation walker is hanging out in the bottom of this low well here. But you want to be able to get from that well to this higher well that's across an energy barrier. And probably what you'll actually want to be able to do is have an equilibration back and forth between them, so you have like the right relative occupancy, so you can compute things like relative free energies. So you can either run that for a really, really long time conventionally, but that can often be difficult for systems that are of interest. Or you can do something like this, where you let the algorithm like jump it from one temperature to another. And as it goes up to higher temperatures, the effective barrier between the states gets lower. You can get exploration back and forth. And then as it goes back down, some of the times when it comes back down the temperature ladder, you'll end up in the higher state. So if you do this sort of thing and then look at your occupancies at the lowest rung of the temperature ladder, you should get the right distribution much more efficiently than if you had just run straight MD. So this is one of the approaches that we offer. Another one is something that we call tempered binding, which we published on in PNAS in 2019. If you consider, for instance, two interacting proteins, and you'd like to be able to explore their interaction without getting caught in kinetic traps, this is the kind of thing you might want to use. So you can think of the interaction between two proteins as being decomposed into a bunch of pairwise interactions between all of the atoms between them. And we're looking just at van der Waals here. And we can then set up a lambda schedule where our bottom Hamiltonian is essentially the normal conditions, which, since this is something of interest, we're presuming that the interaction between the two proteins is fairly favorable in that low lambda rung. And then we, over the course of our different Hamiltonians, we increase sigma, which makes the favorable distance. We increase sigma on these pairwise interactions between the proteins rather than just on the atom's values, which causes the equilibrium distance between them to become further apart. And we also reduce the epsilon, which causes the interactions to be weaker. And this makes dissociation more favorable. And if you run a simulation with this, with time-square sampling, you get visits that go up and down your lambda ladder. And this lets you explore association and dissociation so you don't get sort of stuck in a metastable association that isn't the one that actually corresponds to the one that's likely to be your crystal structure pose. So in the next slide, I'm going to show you what this looks like in the case of Barnase and bar star. So here's a simulation where first we're running conventional MD for quite a long time, nearly 200 microseconds, I think. And you can see that these two proteins have come together first in one metastable pose and then in another. And it's very stable, so this isn't going anywhere for quite a long time. However, if you compare it to the crystal structure, you'll see that it does not match. So this isn't sort of where we want to be. But we were not going to, with any reasonable time scale, explore what we wanted to see. If you instead run tempered binding, which is we're doing at a much lower time scale here, you can see it sort of coming together and moving around and escaping, and then settling for a little time at least into a fairly stable pose, which you can see matches the crystal structure very well. So this let us find that pose. You'd also expect it to see the metastable pose that you saw stably in the first simulation, but you wouldn't expect it to get stuck there in the same way. So this can be very useful if you're trying to really understand the ways in which two proteins interact. And I should also say, while I'm comparing to the crystal structure here, you do not need to have that as input. This is a general approach to modifying the interactions between two molecules. So even if you don't know the bound pose, you could try this and see what poses you explore. And that might even let you find something that might be a good candidate bound pose when you don't have one experimentally. So another class of methods that we offer is the ability to have restraints on the center of mass of a group of atoms or center of geometry, and then also be able to temper those restraints. So you can do this to set things up like having a relative position restraint. Let's say you have a protein and a ligand and you want to pull it in and out of the pocket. You could set up a group restraint on the distance between those two centers of mass, and then use TSS to temper the distance, the equilibrium value of that restraint. And this would both let you explore that moving in and out, and also give you a free energy profile over that distance, which is what I'm showing here in the bottom. Similarly, you can set up an absolute position restraint, which is just saying I want the center of mass of this molecule to be targeted to a particular location and temper the value, like say the X value of that location, which lets you drag it back and forth across your simulation box, which if you, for instance, have a membrane crossing your simulation box, you could use to get a sense of what the free energy profile is of dragging it through that membrane. Again, showing the example here. So lastly, you can also temper the root mean square distance to some reference structure. So you can set up a restraint that says, here's some reference structure, here's some subset of my system. I want the RMSD between that subset of my system and the reference structure to be some target value, which could be 0 if you want to target that structure, or could be a higher value if you want to push away from that structure. An example of something you might use this for is you might want to compute the free energy difference between different conformations of a single system, say. So imagine you have a protein where you have a closed and open version of a pocket or different states of a loop. As long as you have reference structures for each of those, you can set up a lambda schedule like I've shown here, where you say, okay, let's start with a target distance of 0 to the first structure and then increase it, and start with a higher target distance to the second structure and decrease it. And this will let you get the relative free energy between those states with a little bit of work to go from, this is essentially kind of umbrella sampling, to go from the free energy values that TSS reports to ones that account for the kinds of restraint that you've used. So bottom line, we have 4 different kinds of enhanced sampling that are available. Simulated tempering, which is, again, temperature tempering with adaptive weighting to let you get better exploration, crossing barriers more easily. Tempered binding, which is letting you explore different interactions between 2 different molecules. Restraints between centers of mass or groups of atoms, which lets you pull things together and apart or just in space. And then restraints on the RMSD of a group with respect to a given reference structure. For the last 2, as I mentioned a little bit on the earlier slides, you can either, so I didn't mention this. One thing you can do is you can use TSS to control them, which is 0.2 here, which lets you do a form of umbrella sampling. You can also just have a fixed schedule and time. You could say something like, okay, let's start off with this ligand in the pocket and drag it out over time, which is sort of a non-equilibrium, you know, approach that for Jarzynski or something like that. So that's available to you as well. Or you can do this to do sort of umbrella sampling to get information about equilibrium distributions of free energy for particular relative values of the restraints. So those are the 4 types that we offer. I'm going to talk a little bit briefly about how you can see what the results of these runs look like and how to do a little bit of debugging. So we have a tool that's available at PSC called PyTSS_PSC plot basic. You pass it a work directory and it'll output a plot of the following form, which has 4 quadrants. The top 2 quadrants relate to what Hamiltonians are being explored by the simulation that you're running. And the bottom 2 quadrants relate to the reported free energies, reported estimated free energies. So on the top left, this is just a histogram of what rungs are being visited with what proportions in the blue bars. The red bar is an estimate of what TSS thinks your visits should be. So that's what it's targeting. And for debugging purposes, if the blue histogram and the red line disagree a great deal, you should be suspicious that something weird has happened in your simulation. This is actually fine. It's okay for it to be very noisy. But what you might want to see is, like, if a lot of your histogram mass disagrees a lot with your red line location, then you might have a problem. On the far right is the distribution over time of your rung visits. And this one looks good. What you generally want to see is like not a lot of features in this plot. You want to see it sort of like easily going up and down very frequently. And if you see things that look very separated, I'll show you an example on the next slide, that can be a sign that something weird is going on. In the bottom left is a free energy trace over your different Hamiltonians. So this is where if you're doing, for instance, dragging something across the membrane with a group restraint, you would expect to see maybe a spike in the middle where you cross through the membrane. But this is just sort of characterizing what the free energy looks like as a function of whatever your lambda schedule was. And on the far right, on the far bottom right, is the difference between the first rung and the last rung over time with error bars. TSS does online estimation of errors because this is something that one is frequently interested in. For instance, when you set up a schedule to find out what it costs you to go from one place to another in your lambda space. And there's documentation of this and much more detail on the PSC DesRes information site, which I've given a link to below. I suspect there'll be other links available in the chat and on the website.
So Avi, I've got a question from the chat here.
Sure.
So I think the question is, and feel free to chime in if I get this wrong, is replica exchange solute tempering rest also included in any of these enhanced sampling techniques?
No, we don't include rest per se. Rest, but we don't offer parameter tempering, do we? Or I think you're muted.
No, other than the particular parameters that you described.
No, we don't offer rest in this context. Rest is essentially, as the person asking the question probably knows, a matter of sort of locally raising the temperature for a subset of atoms so that they are much more energetic. And you can do this either by literally raising the temperature for those or just by dividing the energies for the energy terms affecting those atoms, which has the same effect. We do not offer that in a targeted way, though you can just do like you could just do temperature tempering, but you wouldn't be able to, for instance, have a ligand in a protein pocket and do rest on the ligand.
Follow-up is, how about REMD if we include all the system in tempering?
So we don't offer REMD, but TSS is conceptually similar in terms of what it will give you. REMD is where you're running one simulation at every Hamiltonian at all times and then doing swaps. TSS is where you're running a single simulation that gets jumped around in space, in Hamiltonian space. We don't offer REMD. But you should be able to get similar behavior from TSS.
Yeah. And then one more follow-up here. Oh, that answers that question. All right. So you got two in one go. And I think that's all the questions for the moment.
Okay.
Thanks, Avi.
Sure. Yeah, and feel free to ask any questions that you have. I'll go on to the next slide, which is my last slide, just to give an example of how you, like, what a poor run might look like and how you might go about troubleshooting it. So this is an example that exhibits several of the problems I mentioned in the previous slide. You can see here that there's a sort of mass mismatch between the blue histogram and the red line. And you can also see on the right that there's what I like to think of as barriers in rung space. You can sort of see that the simulation is having trouble reaching the higher rungs for a region of time, and then once it goes across, it has trouble reaching the lower rungs. And if you see things like that, a good way to go about debugging this is to look at your simulation trajectory and try to spot notable differences in conformation that occur across this barrier in time. Maybe you have something like there is a side chain of your protein that, for whatever reason, your tempering schedule isn't causing to flip, but is dependent on it flipping for you to be able to have a favorable move to another region of rung space. Like maybe you're trying to drag your ligand out of the pocket, but that's an incredibly high energy thing to do until some part of the protein flips out of the way. And if you see things like that, you can try to use enhanced sampling to like change your schedule to help encourage them or change things in some other way to get around it. But yeah, this is in response to a question that we had last year, sort of asking for, some tips and tricks for how you might go about debugging this kind of thing.
That sounds terrifying.
That you get a profile like this, you mean, or?
No, that you have problems like this that you have to debug. Like,
I mean, enhanced sampling sometimes works great just out of the box and sometimes does tricky things. Like we deal with this sort of thing all the time.
I think it's a technique for optimists.
Yes. It's a technique for people who aren't satisfied with what they've got out of the box. Yeah, so that's what I've got. I can leave the slides open if people want to ask questions about it, or I can close them so you can see our pretty faces.
What other questions do folks have? We've got some time to answer any other questions you might have related to anything that's been presented today. So there's a question about the performance of Anton with TSS.
Worse.
It's not tremendously worse, is it?
No, I think if you have a reasonable interval, like you're running every 5 picoseconds, it's probably 80 or 90% of the speed of a swimming simulation.
Okay, so there some performance impact, but reasonable. And when you actually go to set it up, you know, there's help available if you have questions or doubts of, you know, how to make sure to hit the right balance. So Ken just suggested a rule of thumb for how often you're making those
We
swaps.
just throw those numbers into our examples, and then people aren't usually bold enough to change it from our examples. So
There you go. We'll have examples.
is that documentation available before you write your proposal, or only after you write your proposal?
Currently only after. So it's, if you
Yes.
get
Ouch.
Yeah.
if you get on the if you're so fortunate to get on the system, but we have that email address that hopefully is in the RFP. So if you have questions of this kind before, as you're writing the proposal, you know, we're happy to answer those questions if there's any doubts. So feel free to reach out. Yeah, welcome to talk internally, Ken, about just making it all open.
Above my pay grade, man.
I had a quick question on requesting meetings. Is there this is my first time applying for one of these allocations. Is there something specific that we would need to prepare for the meeting to ensure things go smoothly? I guess how specific of a question are you guys expecting for the initial conversations?
We were talking about a meeting. Which meeting are you thinking about?
I believe there was an email on the RFP for reaching out to ensure that the system seemed okay and the questions that we were trying to address scientifically were also a good fit for application on Anton.
Yeah, so any questions like that, yeah, feel free to send. Usually we just, you know, we'll just do an email back and forth, and if it wasn't you know, if there was enough to warrant getting together for a meeting, we could certainly do that. But usually we're able to just address all those questions directly in email.
Okay, gotcha. Thank you.
I have a question for you. Are you gonna join us for the next webinar, which is at 3 p.m. East side? Because we are gonna answer many of these questions. So I suggest you join if you haven't done so yet.
Yeah, I'll be staying on for the next one.
Awesome. Okay, cool. Thank you.
Great. So we got another question about TSS. It says, I want to study how a protein membrane interaction alters a protein-protein interaction. However, the original protein-protein interaction is too stable to make any changes. Could I apply a TSS to proteins, but not on the membrane to avoid membrane disassembly?
So TSS is like you're applying TSS in the sense of you're picking one of these restraint strategies to use, and then TSS sort of governs it for you. So what you might have meant tempered binding. Yes, you could use tempered binding on the interaction between the two proteins, but not on the interaction between the protein and the membrane, because it is targeting an interaction between two molecules. So yeah, that should work fine.
Great. Next question, are there any examples of systems that did not work with TSS, even though it seems like they should have?
Yes.
Yeah, cool. If you got something, Ken, go for it.
I don't have anything specific. I'm a computer scientist, so I have an entire worm's eye view of this process. But yeah, I get error tickets from things where the TSS restraints tear stuff apart. That seems like the main hazard is like you're applying arbitrary forces to things.
Mm-hmm.
But
Yeah.
you're the optimist. Say the opposite, please, Avi.
I mean, I agree with that. If you pull too hard on something that can't take it, like we can't. So I'll say we can't easily use. So TSS is a general approach for going between different Hamiltonians. So what the Hamiltonians are will govern what TSS does. We can't really use we don't have a good TSS strategy for like unfolding and refolding substantial proteins. So if you pull in something hard enough that you're unfolding it, you're probably not going to get it back in its original folded shape. So that's what I give as an example of a failure case. For other things, often stuff is pretty robust. Like as long as you're not pulling a protein apart or something, as long as you're doing sampling that is not going to be irreversible, it should be reasonably well behaved.
Great. Okay. So the next one on the list here is, would you suggest a long MD simulation or TSS simulation for a large?
Intrinsically disordered protein, I think.
Yeah. Okay.
Depends what you're trying to study, I guess. Yeah, it depends a lot on what you're trying to study. If you want to just see, if you want to see more conformations and your IDP has a lot of metastable traps, I might suggest TSS with temperature tempering. If it doesn't and you just want to characterize what's going on, I might say just run long MD. I'm doing my chemist impression here, and I'm not a chemist, but I think that's reasonable.
Wait, if you're not a chemist, what are you?
I'm a computer scientist, man, and a biologist.
And a
Chemist,
biologist.
though. I'm doing the programming here, not the chemistry.
All right. I guess then the last one I see is what force fields are supported for simulations on Anton. And so I could tell you, Sergey, I think we have that pretty much comprehensively listed in the RFP. But I guess folks here could maybe answer off the top of their heads. Or I can look it up real quick to make sure I don't miss
sure. I think we accept Amber and Charm. I guess that's it.
Sergey asks, could one run a simulation with a ligand which is not yet parameterized, and how does one parameterize a ligand for simulations in Anton? The ligand has to be parameterized to simulate with it. Otherwise, we just don't have any interactions we can use. I'll defer I don't know the answer for the other question. Maybe Ken, Vipar?
Does Vipar know about ligands? We have a lot of internal technology for parameterizing ligands that we do not share. So I don't know what people do outside.
Yeah, yeah. So the way the typical workflow is that you'll build the system and come up with parameters in one of the standard force fields. Yeah. So one of the ones that ideally something like amber is ideal. I think if you can get it in an amber force field, then it's easy to convert over to what we use on Anton. So that's great, but you can also we can also translate things coming from Charm and even from GROMACS into what are the parameters that we use on Anton. But I think, yeah, basically it's, amber and Charm is what you want to have for your force field. And then we'll be able to set up the parameters using the tools that are on Anton if you come with a system like that. Okay.